We are going to start in a minute. In this session, what we are going to see some demonstration of how you can use Hugging Face pre-trained models that are available. And so we'll start with introduction of what is Hugging Face and what are the pre-trained models are available, and how you can use them, because training a large language model or a diffusion model from scratch might not be feasible. That might require uh, high computation power and infrastructure. So sometimes for applications you can use those existing pre-trained models. So we will have a small demonstration how you can import those model and access in your notebook, and you can use it. So I'll share my screen of the notebook. Okay. Talking about Hugging Face, so it's an open source AI company. It is basically best known for Transformer library, which is quite popular and which provide ease and access to thousands of pre-trained models. You can access it for various tasks like natural language processing, computer vision, audio, reinforcement learning, and so on. There are some key highlights of Hugging Face. One of is Model Hub. So Model Hub is basically a central repository that hosts all those uh, large language models and computer vision models like GPT, BERT, T5, Llama, Stable Diffusion, and so on. There is important library called Transformer, which basically simplify the use cases so that you can use those models that are there in this library. There is another library it provides called Diffuser library, and that basically used for image generation. And one of the popular model is Stable Diffusion in this. There is a separate library called Dataset library is also there. You can use uh, thousands of datasets that are available on this dataset library from the Hugging Face. So you are going to see in 2-3 notebooks that I am going to demonstrate. You are going to see for some notebook we are using Transformer library and or Diffuser library in case of a Stable Diffusion, the demonstration that we are going to see. So I hope my voice is clear and everyone is here to start with. So we can start, right? It will also be good that if you do this hands-on together and write the code. So what I can do, I can share this uh, collab file in the chat. So what you can do, you can just open it and create a copy of it. Instead of editing the main window, you just copy and uh, make a copy of it. For that, go to file, just create a copy, save a copy in the drive, then it will create another copy of it. Okay. So in this particular example, what we are going to do is we are going to build a we are going to use a pre-trained model for text to image generation, and this particular example uses stable diffusion based model. And if we start with, so this, because we are going to use diffusion based model, so we use diffusion library. So here in this case, here this particular line of code basically so these are the abstraction provided by the Hugging Face, like diffuser or transformers. And using those abstraction, what you can do, you can load the pre-built pipeline. Here in this example, we are importing, so we are going to use diffusion pipeline to import a pre-trained model. Using this, you can import a particular model. So in this particular cell, so let me run it. So for example, I'm running this particular cell. Also make sure you connect to GPU. So you can change the runtime. It is already connected to GPU. Now in the second part, where we are actually loading the pre-trained model, which is stable diffusion Excel base 1.0. And if you see, some parameters are also there apart from the model path. Cross type, which basically we are using cross.float16 for basically we are using half precision for speed and memory efficiency, and we are keeping use safe tensor true. That ensures that we are using safer model, so we are loading safer model, and the variant that we are using floating point 16 float 16 format. And this pipe dot to CUDA, basically it moves the entire model to the GPU. So we are loading the model and we are moving the model to GPU so that the inference time will be minimum. So if you just pick it and if you run it, that will load the model. There's one more thing. Sometimes for some pre-trained models, you might face access issue because different models are provided by different companies. So you might have to log into Hugging Face and create a token, and that token you have to give it here. So this stable diffusion based model is available publicly, so you can directly use this. So that when it is loading, until it is loading, let me explain what this particular stable diffusion model, how it works. So we are talking about a text to speech model. So this particular pre-trained model, how it works, so it takes a user prompt. So whatever you write, let's say you are writing some user prompt that you as a sentence, then this uses a frozen text encoder. So this encoder is provided by OpenAI, and this basically encodes and create the sentence into a vector. So, and it is written frozen means we are using freeze text encoder. We are not changing its embedding. So it is not trained. Weights are fixed, and we are just getting the text into fixed length vector or fixed length text embedding usually. So this particular model is we are getting 77 into 768 text embedding, and then there is another input. It takes latency. Basically, generation of the image starts with a random noise sampled from this normal distribution, and this noise is basically currently it is in. So you can think of it is in the latent space, not not the pixel space. So we are going to convert it into this. So this we have 64 cross 64 latent space. Though it is not shown here, there might be channels of latent. So 64 cross 64 into number of channels you have, and this is basically the main model, which is main neural network that basically predict the noise to remove at each step. So earlier in 2 sessions you have understood how diffusion model works. So each in forward phase you add the noise, and in the backward phase, in the reverse phase, you predict the noise. So this is the main neural network unit, and we are calling it text condition latent unit because it is also taking a text embedding. So that it takes input a noise, which you can think of as a noise image, and the text embedding that is coming from the yes. So that here unit is actually working as a reverse model that performing the reverse process in the diffusion task. So, and there are three inputs basically. One is you can see here, one is the noise, and so it is run. So okay, it has run. One is the noise, and one is the text embedding, and the time step. And the output is basically the predicted noise at time step t. And so what happened at each step? So it is done for some n times, or you can you can you can assume t times. It repeats, for example, 50,000, etc. At each time step, what it does, denoising happens with an unit, and the scheduler algorithms, for example, DDIM or any other that is used in the diffusers, update the latent based on the predicted noise, and that basically we have seen in the previous 2 sessions then how this happens. And the condition latent that you get final output after all the reverse step, you get this final latent vector, and that represents the denoise image. Still in the latent space, we need somehow we have to convert into pixel space. For that, it uses variational autoencoder that basically convert this 64 cross 64 denoise image into full 512 cross 512 output image. This is how the pre-trained model that we have loaded is generate the image based on the text prompt. When you run this, you will see the pipeline, the whole pipeline, what it contains. It contains clip tokenizer, text encoder, diffuser, and variational autoencoder. So once it is loaded, so it is quite easy to use pre-trained models from Hugging Face. You just load it, and once you have loaded it, you can just use model to generate the image. For example, here the model is loaded into pipe variable. So using that pipe variable, uh, you just pass your prompt. When you either you can directly write this prompt here, or here we have a variable prompt and we have written please generate a beautiful landscape of Himalaya. And that prompt, when you give it to the pipeline, it generates a list of images, and through those list of images we are taking the first image, and that goes to the image when you run it. So that when it is run, you can see the image. So that will create a beautiful picture using diffusion model of landscape of Himalaya. You can give any prompt. Let's say uh, a horse with the wings. Let's say what it generates. Meanwhile, parallelly, I have shared the link. You can copy it, create a copy, and you can experiment it with. You can see it is generating uh, a horse with the wings. So, so you can write, you can use the pre-trained model, and you can use it. It is quite simple in Hugging Face. You have to just use those model, and on the top of it, you can create. So you might be doing some mistake in the. So have you run this the first line? You might not have imported it. You have to import it. Or see if you have. I mean, is there any spelling mistake, or is it resolved? Or you can share your screen as well. Okay, it is resolved. Okay, fine. Okay. On the top of it, if you are creating an application using web application using Streamlit, so you can use the pre-trained model from Hugging within few line of codes. How many of you are trying? So there is another model we are going to see. We are going to have we'll import a large language model, and then we are going to see uh, how we can use it. Let me share the second. In this example, we are going to use a large language model. So let me share this notebook as well in the chat. Just make sure you copy it, do not change it into the original. So I've shared another notebook. So you can explore different types of text to image. So we have not used any data set because the model is already pre-trained. So we are just using the pre-trained model, which might be, so this particular model you can explore on which type of data it is trained. So we are just using those pre-trained models from there. So um, there might be a case where you want to fine tune those models, right? So based on type of problem you have, type of data you have, you can access those pre-trained models and then you can fine tune it. There is another example. Is it visible? Second tab, pre-trained LLM. Okay. Here, if you can see here, we are installing transformer. It's okay. So I have to cancel. I have to stop the session here. Disconnect. Because free version uh, will not allow you to run multiple sessions on GPU. And it is loading. There is a line, there is a login code here. If you are using any pre-trained model which is not publicly available, then you have to log in via providing the token from Hugging Face. So if you go to Hugging Face, uh, you have to log in. I'm already logged in this. So when you go to the account, you can see access token here, and you can create new tokens. When you create a token, you get a token ID. You give the you can give the token name, anything, and appropriate settings. And when you create a token, it will give you a token that you can use it. So for other models apart from publicly available, you have to log in. So then you have to run this line of code. So when you run it, once it will be completed, you will see here it will ask for the token. However, for some publicly available model, you don't have to perform those steps. So it is asking for the token, and you can put the token and you can access it. However, in this particular example, we don't need it. So because we are using when pre-trained LLM model, which does not require anything. So when you work with the language models, you might have seen in the previous sessions that the text, we always tokenize it. So when you are using any pre-trained model, you have to use the tokenizer as well. So we are accessing both the tokenizer and the model. And when you so tokenizer is available in the auto tokenizer, and the models are available here. You can just change it. You can access any llama based model as well. However, for llama based model, llama models, the models that are provided by OpenAI, you might have to provide the tokens. Once it is loaded, you can just write a prompt and before uh, creating the output, you have to first is it, and then you can create the output. And that takes some of the, so using the model, you pass the input, number of tokens it should generate, maximum new tokens, the temperature, and those values. You might have uh, seen that these things are discussed in the last session of prompt engineering yesterday. So when it generates, it's basically the output is the tokens. From the token, we have to decode the text. So for that, from the tokenizer, we are using decode, and we are passing the output. Again, it generates a list of output. We are passing one output, and that will print here. So you can see we have written a prompt, write a short poem about AI in nature, and it has created a poem out of it. So I have sent you both the link of both the library, both the notebooks. Please run it, and when you are done and you think it is working fine, there is no issue, you just let me know. You can write yes or no. Then once you all are done, then we will move ahead. This Quen is also basically um, is a product of Alibaba company, like GPTs and Llama. So Llama models are from OpenAI. Once you are done, just write done, then I will move ahead. What was the question? Grok is also, yes. Grok is also model. DeepSeek is there. Grok models are also available, I think, on our Hugging Face. So large language model, you basically you have to import both the things, tokenizer as well as the model, because uh, the tokenizer that model is using, we have to use the same tokenizer for the input, for the tokenization of the input as well. Now let's okay. Since if you're not using a pre-trained model and you want to train your own let's say image generation model, uh, which is based on diffusion model pipeline, uh, I have one notebook to show you, and I'll explain everything there, what is there. Mm, okay, so this particular example does not use Hugging Face for any pre-trained model. Instead of it trains diffusion model. So for in this particular example, we are taking a data set from Kaggle. So you can see this particular line of code, basically downloading a data set from Kaggle, which is anime face data set. So and this particular line, this gives you this line, download the data set from the access the data set from Kaggle Hub, and you get the path of it. This is printing, so where your data set is there, is printing here. Let me just stop the previous sessions so that it can. So if you the first line, if you see it is uh, download the data set, and this is downloading into your some uh, cache repository, local cache directory, and the path of it is you have the path of this now. So let me now downloading the data set. So after this, uh, the download data set, we need to uh, pre-process it. So this particular line of code, uh, if you see here, we are using transform from torch vision. So this particular cell, if you see, we are basically pre-processing the loaded data set. So this we are the transform, basically transforming, cropping the all the images into 64 into 64, and we are loading the data set using using train loader image folder. Usually when you have a face detection problem where you where you have a, let's say, classification task, cat and dog. So what basically this image folder do, it creates a folder and for different class and put the images into it. That's how this data set is organized here. And all the data set we are going to have a base size of 100. Right. So this image folder will create and create a label for all the images with the folder name. So in this particular example, we have only have the faces, so it will there is no multiple labels here. We are just having the anime faces. So this basically transforming into 64 into 64. So it is cropping the image, and after cropping, we want to only take the faces. So we just want to take the 64 cross 64. Acha, haan. Okay, yes, I'm sharing it. And this particular transform resize the size image because we want to train our model on a small size of data, obviously due to the completion limit, and all basically the existing okay, so this is the link of this. So after performing this basic pre-processing, you have a data set, and you can it is divided into base size of 100. Now in the next, this particular code is nothing but we are just exploring the data, how it look like. Because we are just visualizing it. So this is how those anime faces looks like. And the whole objective of our model is to build a model that can create similar images for this. So if you need any explanation for this, so basically we are accessing one batch of images from the train loader that we have loaded, and for each batch we have a data in the target. Obviously in this particular example target you have only one because they all belong to one class. We are printing the shape, so you can see the shape here, and then we are creating a grid of first 16 images in it, and once it is shows the first batch, we are just breaking it, so we are not continuing in the loop. It is just showing the first batch of 16 images. So this now after displaying those data, okay, so this particular cell, what we are doing, we are setting up the diffusion hyperparameters, like including the number of steps, how noise is added each time, that is the beta schedule, and you compute derived value like cumulative product of alphas that are needed for the forward pass and so on. So this basically gives you here. You're all setting up those parameters for diffusion. Particularly, if you see here, we are having number of time steps 1000. So normally a common setting in denoising phase, and beta start is 0.0001, beta end is 0.002. You might have seen those values in the first session as well when Dr. Ashish was explaining everything in the theory part, right? Then you have alpha value. So you are setting the alpha value, the portion, basically the image that retained after the noise is added, and this alpha 1, alpha 2, how it is basically how the image is survived after the time step t. And we have defined one helper functions to compute the noisy images xt given x0 and t. So this is the setup part that we have. Right. So in this particular cell, what we are doing, we are initializing the forward diffusion process. And the second phase, which is the denoising phase. So now we are defining our denoising model, and here also we are using a simple unit architecture with which will predict the noise that is added to an image at a given time step during the diffusion process. So it is same as what Dr. Ashish have explained in theory. So it defines a simple unit like CNN model, and it takes a noisy image and a time step, and it outputs the predicted noise for the time step. We are defining this model here. So after defining this model, we basically next what we are doing, we are here we are having a training loop for the model that we have defined. So we set up the optimizer. Here we are using the atom optimizer and the loss function and the learning rate and number of epoch for which we will run, and the model is trained for each batch in the image. We add the Gaussian noise and use the model to predict the noise. We are using the model to predict the noise, and after this we calculate the loss and we perform the back propagation and update the model weights. And we are logging the training loss after each batch, each 10 batches. So if you run this, the training will start, and for each epoch you will for each epoch after 10 batches you will see the loss value. So Dr. Ashish has also shown one of the example of diffusion model. This you can think of a model on a custom data set. You can use your own data set as well. You can pre-process it, and you can train your own model. So, and it is running. This particular cell is basically for the sampling and generation loop. When you use your trained model to generate new images from pure noise, this is basically the reverse of the forward diffusion process. So you start with the So you start with the pure random noise. You then iterate over uh, to basically you iterate to denoise the using your train model, which is this. You have access it and you predict the noise, and you then update uh, the values, and then once it is done, you generate, it produces the realistic image towards the end. So once this loop is completed, and then this particular line, these particular line of loop code, nothing but it is just showing those uh, samples generated. So we are taking the 16 sample to display. Once this training will done, uh, then you can sample it. So you see here the samples are generated. However, these samples are not exactly looking like uh, the original images, because we are not training it for a large amount of time, and we are not training it for maximum number of epochs. We have just used 5 epoch for the demonstration purpose. So after 5 epoch, it is generating something like this. However, we had actually trained it and we tried it to train over more number of epochs on a server, GPU based server, which is trained over 2000 epochs. And after training the same code over 2000 epoch, it is somehow trying to generate those images. So it will require uh, more number of training to generate a similar images as of the data set. I've shared it, right? I've shared it. You just walk through it, uh, open it, create a copy, and walk through one by one. And if you do not if for any line, if you have a doubt, you can just ask me. I'll explain what exactly that particular cell or particular line is doing. Training is done. Uh, Sampling, it is showing the birth images, not exactly look like anime images, but still after 5 epoch, you would expect the performance will be very poor. So should we move ahead with the next? So yesterday we had a I've shared a notebook for language model for predicting the next word in the sequence and using LSTM model. How many of you have tried and run that particular notebook? If not, I'll explain what exactly that particular uh, notebook is doing. So anyone is trying? Yes. Uh, it will uh, it will take time. So uh, no, so the code that you have run for text to text, it has to be run on the GPU. Then it will take lesser time. You might be running on the you could have changed the uh, machine instead of CPU. You have to run on the GPU. So runtime up, you should have changed the runtime. Then it will take a lesser amount of time. This was the code that I have shared yesterday, text to text. This is I've already shared to you on the WhatsApp group. What I will do, I will download those notebooks and I'll share in the WhatsApp group as well and the canvas as well. So you can tweak those notebooks. You can change and see what exactly it is reflecting uh, as a change. Let me disconnect this. So you can change the runtime. So you have to. Okay. So in the free version, we have an issue of users time limit. It might have I might have overused it. So you can run it. Let me explain what we had done in this example. So we have built a language model that predict a next word in the sequence using the previous words, and we have used the LSTM based model. So one second. Okay, so let me. No, okay, fine, run over. So this particular line is starting with. So we are going to train over one data set. So there are some data sets available, and in the start of the session, when I was introducing Hugging Face, there is a diffusion library, there is a transformer library, and there is a datasets library. So this particular line, basically, we are uh, collecting the data set, and the versions is 2.15, and we are downloading those data set. And then because we need a tokenizer, so NLTK provide one tokenizer. So there are different version. A simple one is func and hyphen tab, or you can just only write func as well. So that gives you the tokenization that is going to use tokenize the text. This is in this particular cell. Basically, we are uh, importing the libraries to load data sets. From data sets, we are importing load data set to load one particular data set. From NLTK, we are importing word tokenize to tokenize this. And basically to create, so all these imports are basically to create data sets, manage batches, and split into training and testing. We are using random split. This particular line basically coming from Hugging Face. So datasets is a library that is provided by the Hugging Face dataset library, and using this you can easily import or load the dataset like IMDb dataset, Wikipedia dataset that is already there. So here what we are doing, we are accessing one particular data called IMDb dataset, and we are building a vocabulary for our LSTM based language model. So this particular line is basically loading the dataset, and the split that we are only using for training purpose. So training part we are loading. Then with this particular line of code block of code, what it is doing, we are using word tokenizer for each review that is there in the dataset. So IMDb review dataset में for each review, what we are doing, we are creating the review tokens, and this is optional. We are just counting how many tokens are there, and we are keeping all those tokens into database tokens. So we are building a vocabulary in basically all the tokens that are there in our text in the database tokens. And over this vocabulary, we are creating a class to ease of access those vocabulary. So we are defining some functions. We are creating a mapping that word to ID and ID to word. We are creating this. And for example, let's say particular token like movie is there at particular index 57, or so this particular line of code basically mapping from ID to string or string to ID. So each point of time we can map with ID or word to ID and word ID to word. And we are providing some key methods in this class. For example, if we have a token, a particular word, we want to retrieve the index of it. So that get item is a function. We have index and we want to retrieve the token. Then there's a two tags is there. We want to find out the length and so on. So this for unknown, we are going to provide some default index. Once you run it, you will, if you see the vocabulary size was 49447. So this is till this point of time we have created tokens. So from accessing the data, we have created a vocabulary of 49,447 tokens. Now, from this vocabulary, we are going to create a data set, and which is we are having a we are working on a problem where we are predicting the next word. So we are creating from this vocabulary, we are creating a 6 grams tokens from these tokens. 6 grams means a list of 6 tokens, where initial 5 tokens will be act as an X, and the next 6th token will be act as a Y. That will be used for training. 5 as an X and 1 is for Y. Right? Means 5 will be your on which training will happen, and it will predict the 6th token. So we have pairing of X and Y. We are creating the 6th token. So this particular line creating the n-grams. N-grams. This list will contain list of 6 grams. So for example, once it is run, you can see now the data set length is this. Example n-grams like 2, 3, 2, 4, 5, 6, and next. So we are just printing 2 n-grams. Inside this n-gram list, we have 6915344 n-grams. And obviously, so these are basically indexes. So you can always convert these indexes to text or text to index using the class functions that we have created. So you can see the same examples are in form of text. So I rented, I am curious yellow, and from. Now the next token, next n-gram, 6 n-gram is shifted by 1. So this starts with rented, and there is another next token is there. Right. So we have created this data set so that we'll train our model, and when model is trained, it will predict next token based on the previous system. Now we got the n-grams. Now we have to create our data in a particular format so that PyTorch can train over it. So we are creating tensors out of it from those n-gram list, and from those tensors, we are splitting X and Y. So we are keeping 5 tokens as a X and last 1 token as a Y. The overall size was this. Since from this initial 5 token from each n-grams is taken as an X, the last token is taken as a Y. So the size of X is these many data set. You can think of these many rows in the data, and these are the tokens. And a corresponding Y that it will predict, we have these many, because there is only one Y. I hope you are following me. And this particular, basically, we are from that particular n-gram data set we have created, we are splitting into training and validation part. We are keeping 90% of the data as a training and other 90% as a testing. And next, what we are doing, we are creating a data loader for training and the validation set. And this is basically a standard PyTorch step for feeding the data into the model in a batches. We are creating batch size of 1024 out of this data. training and validation. So training data will also be divided into these many batches in some batches of size 1024, 1024, and this will also be divided. Till this point of time, what we have done, we have loaded the data, created a custom class to ease of access to change, get the index, get the words, and so on. Some helping functions we have created in a class, and from that particular data, we have created n-grams. Particularly, in this example, we have created 6 grams, where initial 5 tokens will be act as a X and next token will be act as a Y. And these two again steps to create dataset object that is becomes easier to train the data, train the model, and then we have splitted the data into training and validation till this point of time, and we have created data loaders, but in a batches the model will be trained. Till this point of time, we have prepare our data to train our model, and next we define our model, which is LSTM based model. This particular model is MNIT 1. So in this model, it takes a sequence of 5 words, indices as an input, and learn to predict the next word. That is basically the 6th word. So this is basically a standard next word prediction task using single layer LSTM. So we have only one layer. So this is basically just a forward defined for the forward pass, and this particular cell is initializing the model by initializing the embedding dimension, hidden layer dimension, and the model initialization, where embedding and hidden dimensions are specified, and the loss and the basically the optimizer. So in this particular cell, basically we are setting up the model loss function and optimizer. 1 second. I'm stopping for a minute. Okay, sorry. Yes. So where were we? So we defined, we initializes the model, and then next we define a function to calculate the validation loss, and the training is a training loop is defined for X and Y. So after train, so this particular example was shown only for one epoch. If you run it for one epoch, then this will run for one epoch, and you can increase the epochs as well. And this function, basically, once we have trained it, this function is going to use to give the sentence, and we are predicting the next word. So that once it takes the sentence, it tokenizes it into words, and then model, using the model, take the input and predict the output. So, and those from predictions, here we are showing top five predictions. So once you call this function, let's say you are passing a sentence like when I went to see. This argument is nothing but for the next up to next word, how many predictions are there. So you can see when I went to see, it has given 15 output, right? And if you see each output, the top five words have been shown. So this the with the maximum probability that when I went to the C, the, and the next iteration, went to see the becomes the five tokens, and the next prediction is movie and dot, and then the film is a good movie, and so on. So this first column shows the most the top word predicted in a sequence. It started with when I went to see, and the model predicted the movie. Full stop, the film is a good movie. Films, full stop, I am not sure, and so on. And the second and third word, these are the second highest appropriate word to find out. So I have run it for the one epoch. If you run for the multiple epoch, you can draw the training and validation loss over epochs. So I'll suggest you to see and run this particular code. You connect to GPU, then it will run faster. So I have shared earlier. Let me share it again. So this was the third demonstration that we have seen. Since large language models training from scratch is not possible to show in a Google Colab, it will take huge amount of time. So with the restricted time, we have shown till here. And I would suggest you to go those notebooks and try to run and try to understand how it is doing. So still we have a time. So if you have any question from here or the previous sessions, then you can ask. Or I'm here. You can, if you are implementing it, then let me know. I'll I would be ready to. I will help you in the implementation part. Particularly one question that I remember that someone asked me in one of the previous session was on the transformer. So when we are discussing transformer, someone asked me about vision-based transformer. Right. So is he or she is there who has asked this question? transformer which were originally designed for natural language processing tasks for text processing. This, however, have been used for image computer vision as well. One of the popular well-known vision transformer is VIT. Most of the things remains the same. In original transformer, we have an input of words like W1, W2, W3, W4, W5, and we create embedding out of it, and then we add positional embedding to get position aware embeddings. Right? This was the input in case of normal transformer. In case of images, image is a grid of pixels. There is only difference in terms of how the image. Basically, the idea of applying transformer on the image was to convert and somehow map this image into embeddings so that this can be given to the transformer. So we have to convert this input. So there are some initial extra steps are there, like image patch. We create patches out of it. So for each image, so not patch, okay, patch. So the example, let's say input is image is 224 into 224. The whole image is divided into fixed patches. For example, let's say patch size is 16 cross 16. So the whole image is divided into this. So this will be something 224 divided by 16 will be how much? 14? 14 cross 14. Yes. So each patch will be 14 cross 14. So each patch will be 16 cross 16 size. And you will have 196 patches of it. And each patch will be a small square. So is it visible? So my slide visible? So, oh, okay. Okay, so I was explaining how transformers are tweaked to use as a vision transformer. So basically, we transform our input into patches. So now each patch, let's say the example was 16 cross 16, that contains the pixel value. So we have a 16 cross 16 patch, and we have these many patches. And if you have a instead of grayscale image, if you have a colored image, then you will have a RGB channel. So you will have 16 cross 16 into 3, which basically have how many? 768 values. Right? Yes. So for this patch, for each patch, what we do, we flatten out of it into 1D vector. So 1D vector of how many size? What will the size? 678. And once we get the vector, we pass it into some let's say a linear layer is there. We pass it into this, and the parameter of this layer would be learned, and that gives you a fixed length of vector, which is basically our embedding. So we, in short, what we have done to create the input for transformer in VIT, what we do, we from images we create patches, and from these patches we, for each patch we flatten out this. It could be a, let's say, will be two-dimensional matrix. We flatten out to one-dimensional, assuming, let's say, the previous example is 678 value. We pass it to some linear layer, and we get an output. Let's say we assume that we are creating an output of 678. So this basically our becomes the embedding for a particular patch. Similarly, for each patch, we create an embedding, and this basically will result to a sequence of embedding, each one of having 768 size. So you will have 196 such embeddings for 196 patches. Now, initially when the image was there, we have some position information. Okay, so these pixels are near, this pixel are far away. But once we created the patches and we created embedding, the positional information is now lost. And so what we do here also, we add positional embedding, positional encoding to this embedding to get the position aware information. And similar to the transformer that we have seen, this positional embedding can be generated using sine or cosine functions. And if assuming, let's say, VIT, normally vision-based transformer, in case of when we are talking about images, we use for classification or classification tasks. We do not use for generation of images. So if you are, let's say, if you are applying VIT for classification of images, image classification task, so for each class you create one token. That token could be considered as CLS, often called CLSCA. You might have heard about this in a transformer like BERT. To prepend this tokens to the sequence of patch embeddings. So then for each embedding collection of 196, you add one token as well. So now you have a result of 197 tokens. 196 up, you have the embeddings, patch embeddings, and one CLS token for the class. This is optional if you are going into the classification task. And in the encoder part, this sequence of patch embedding with the positional embedding and optionally that CLS token, what we do, we fed it into standard transformer encoder, the one we have discussed in the previous session. Similarly to NLP transformer, this SMS, we have just converted the input out of it. And encoder again consists of multiple layers that we have discussed, like multi-headed self-attention, add and norm, feed-forward network, again add and norm, and repetition of all these layers that we had discussed. So possibly in this case, output of the layer towards the end is basically your CLS token after the transformer layer. And For other tasks like image segmentation or object detection, we can use those patch embedding in between these layers. So if we talk about difference of vision-based transformer with NLP transformer, the original transformer, one is the input representation. So instead of words and tokens, here the inputs are the image patches, and these patches basically helps you to think of image as a sequence of patches. And one of the important thing is, in case of image, you don't have a decoder architecture. You only use encoder side. So for classification, only the encoder is used. A decoder might be used for generative vision task. Normally, we don't do this with VIT, which is very less common. I don't know if someone has done this or not. So this is basically the layman difference between the vision-based transformer and normal transformer. So that's the end of my session. If you have any question, then you can ask. Apart from these, the question that I have explained, if you have any question from the previous sessions, you can ask. No question, then thank you. We are ending this session, and next session will start at please share. Okay, so my email ID is I have shared it on the chat. Okay, so even in future, if you have any question, you can just write me a mail. I have provided an email ID, and now we are ending the session. Thank you.